Okay, so lecture 10 will be on this topic, which is on chapter 3. Basically, the topics of chapter 3 will be on Fourier transform. So for this lecture 10, we are going to cover two main topics. The first one will be on introduction of Fourier transform, and the second one will be on the properties of Fourier transform. Yeah, so we're going to see what are the important properties of Fourier transform, which will be used later in lecture 12, yeah, when we learn about the application of Fourier transform, yeah. Right, so this is the excerpt from your course information, the CI. So basically for our lecture number 10 and 11. And if you can refer to the Google Classroom, so I've uploaded two lectures for this week, which are lecture 10 and lecture 11. So basically both lectures will be covering the topics of Fourier transform theorems and properties, yeah. Because there are quite a number of properties that need to be understood, yeah, and it is very important for us to understand the properties first before we proceed with this next topic, which is on the application of Fourier transform, yeah. So we expect to finish this chapter 3 within 2 weeks time, hopefully. Okay, and this Fourier transform will not be covered in your test 1, yeah. It will be covered in test 2 later on. Right. So from what we have learned in chapter 2 before this, yeah, chapter 2 is on Fourier series. We have learned that Fourier series is a method of representing a periodic signal, yeah, in which we have learned that any form of periodic signal can be represented by Fourier series, in which we can write the periodic signals in a form of sinusoidal forms, yeah, equations. Right, and basically from what we have learned in Fourier series, all of these periodic signals can be represented in terms of its spectrum, signal spectrum, in which we can actually know what are the components of the signals, yeah, in terms of its frequencies components, yeah, so we can know what are the frequency components that exist in the signals. So we can know, let's say, for example, signal of xt. So in xt signal, we can know how many frequencies that we have, and we can actually know what should be the amplitude and also the phase of these frequency components. Yeah. So in other words, we can see that Fourier series, or I can say the source spectrum, is a way of representing the Fourier series in terms of its frequencies values, yeah, of frequency component. All right, and we have, I think I've informed you in class the importance of frequency domain analysis, in which in electrical engineering, most of the analysis that we're going to see later on will be based on frequency analysis, yeah, because it's easier for us to know what are the components of the frequencies that exist in the signals. Okay, so that is for the case of periodic signals. But what if we are given, we are facing a non-periodic signals, in which in a real scenario that we have in the real world, most of the signals that we're going to see are actually a non-periodic type. Okay, yeah. So we can see now the scenario. Previously, when we learned about the Fourier series, it's all about the periodic signal. But now we have a case whereby in a real situation, most of the signals that we're going to see in our life will be non-periodic. Okay, so if that is the case, so Mr. Fourier have come out with a mathematical analysis that produce a new method of representing these non-periodic signals in a frequency domain by using a new transform, which is called as a Fourier transform. Okay, so Fourier transform basically is a way in which Mr. Fourier represent a non-periodic signal in a form of frequency domain. Okay, so hopefully by now you can differentiate between a Fourier series and also Fourier transform. So basically both are similar, yeah, because it is a way of transforming a signal from time domain to a frequency domain. But Fourier series is basically for a periodic signals, and Fourier transform is for non-periodic signals. Yeah, so that should be the difference between the two. Okay, so let's have a look at the derivation, which is based on the based on mathematical equations developed by Mr. Fourier. So I'm not going to be teaching this in depth because it is too mathematics for us. But hopefully, if you're interested, you can have a look at this mathematical proving. Yeah, basically, Mr. Fourier derived this from Fourier series. Yeah. Okay, so this is the equations of Fourier series that we have seen before, which is based on the third type of Fourier series equation, a complex exponential type. We have the xt written to be this equation, which is a summation of n from negative infinite to positive infinite. We have Cn, and Cn is a Fourier coefficients, exponential Jn omega naught t. So mathematically, the Cn can be written as 1 over the period t, integration of 0 to t xt exponential negative Jn omega naught t dt. Okay, this is the equation for the Fourier coefficients. Right, and this is for the case of a signal xt, which is a periodic, yeah? So if we consider a case whereby xt, yeah, xt is now a non-periodic signal. So for a periodic signals, the signal will repeat the pattern for every t, yeah? For every t period, the signals will repeat the pattern. So this is a periodic signals. But for the case of non-periodic signals, we can say that this t basically will be approaching infinite. So when the t is said to be approaching infinite, in other words, we can see that, okay, this is the case whereby the signal xt is normal periodic, but it is a non-periodic. Yeah, so for a non-periodic, the t will be approaching infinite. Okay, so I hope that you can try to figure out on this mathematical analysis that shown, yeah, it can be shown that if your t is approaching infinite, the Cn will be approaching 0, and we can further on say that the n omega naught will be now equals to omega, or approaching omega, and this will be the transition from a periodic to a non-periodic. So this will be xt, yeah? Sorry for that. This should be xt, yeah, which is a transition from periodic to non-periodic. So the transition will be shown by the way and the value of t, a period which is approaching infinite, the Cn which is approaching 0, and this n omega naught will be approaching omega. Yeah, the n is represented, it basically is the line of spectrum. Okay, so there should be no more line of spectrum. So the spectrum will now be a continuous spectrum. Yeah, no more discrete spectrum that we have seen before in a Fourier series. Okay, so in that case, we can come out with the equation of Fourier transform for a non-periodic signal xt, which is given by this equation, yeah, where if we have the xt, the Fourier transform for it, which is given to be in this symbol of x omega. Okay, xt is in time domain. So when the xt is transformed to a frequency domain using the Fourier transform, its frequency domain terms can be written to be this symbol, yeah, x omega, x capital, and the omega is the symbol for the xt which has been transformed into frequency domain, yeah, right. And this is given by the integration of negative infinite to positive infinite of xt exponential negative j omega t dt. Okay, so basically it's almost the same in terms of the equation, but there are few changes on this integration equation or terms. Yeah, so again, if you're interested on understanding this transition, you can refer to the mathematical in-depth analysis of Fourier transform. Yeah, okay, right. So this is the equation that we are that basically explain on the transformation of xt into x omega. Right, so like what we did for Fourier series last time, in which we have this integration, yeah, remember in chapter 2, these Fourier coefficients can be obtained by the integrations, right? Okay, so as I mentioned before in chapter 2, you are not going to be tested on the integration. So likewise, in chapter 3, you are not going to be tested on the integration. Yeah, so that will not be in our scope. Yeah, by right, we are going to use a table as usual. Yeah, use your table. And I believe that I put it in the Google Classroom in our notes, yeah, for this lecture. You're also going to use the table quite frequently in this chapter 3. And this is the case of inverse Fourier transform, in which if we can transform a signal from time domain to a frequency domain, from xt to x omega, so likewise, we can get back its time domain signal from the frequency domain signal by using this inverse Fourier transform, okay? And this is the equations that give us, that enable us to find out the xt back from the x omega, yeah? So basically from the previous slide, if we have xt, when we do a transformation, we're going to have x omega, that will be the equation. And if you want to get back the xt in time domain, what we did is we just simply do the inverse of a transform on the x omega that we have. And this is the equation that enable us to find back the xt, or obtain back the xt. And again, this will not be tested on you, yeah? So just to show the equations, yeah? Just to show the equation that relates the xt in time domain and the x omega in frequency domain. Okay, hopefully you understand this clearly, right? So as I mentioned before, you will not be tested on mathematics, on the integration to be exact, yeah, not on the integration. And we are going to use a transformation table as provided to you in our Google Classroom, yeah, right. Okay, so this will be the properties of Fourier transform, which will be learned in 2 lectures, lecture 10 and lecture 11. Yeah, lecture 11 will be basically dedicated to understanding, learning on the properties of Fourier transform. These are the properties that shall be understood. Yeah, we are going to have linearity, time shifting, time scaling, and frequency shifting and modulation. Okay, so up to frequency shifting and modulation. So these 4, the first 4 properties will be covered in lecture 10, and the rest 4 properties will be covered in lecture 11. Yeah. So for today's lecture, we are going to cover only up to frequency shifting and modulation properties. Okay, so let's have a look at the first properties, which is on linearity. Okay, we are given these signals in which if we have the xt, so it is common for us to have to show that if the xt is transformed to the Fourier transform, it shall be represented by this f. Yeah, if we have an arrow, and on top of the arrow we have the f, so which means that the xt is said to be transformed into its respective Fourier transform signal, yeah, or frequency domain signal. So xt will be Fourier transformed into x omega. Okay, so this is common way, yeah, of writing a Fourier transformation. And yt is also transformed into y omega. Okay, so we have 2 signals then, xt and yt, and both are having a Fourier transformations of x omega and y omega. And we have a amplitude scaling of xt, let's say a. So the thing with the Fourier transform will be simply the same multiplication with the amplitude constant, which is a also. So axt will give us a x omega. And also for the yt, if we have the b multiplied with yt, its Fourier transform will also be the same, which is b multiplied with y omega. Okay, so this is the case if the signals is said to be linear, yeah? And somehow, if both axt and byt are said to be added, yeah, we have axt plus byt, so both are added. So this respective Fourier transform is simply ax omega plus by omega. Okay, so this is a linearity properties, yeah? So the Fourier transform do obey a linearity properties. Okay, basically you can refer to these properties in our table, yeah. So allow me to refer back to the table, yeah. I'm going to refer to the table now. Okay, so this is the one. This is a table that I think I put it in the classroom. Okay, so we have 3 pages of this table, in which the first page of this table or attachment is the properties. Yeah, properties of a transform. It's a complete version of properties. Okay, this we have a linearity, we have a symmetry, a time shifting up to the multiplication by t. Yeah, but there are few. Only we're going to cover only few properties. Yeah, and then for the second and the third page, yeah, second page and the third page, basically these are the full transform of the respective time domain signal. Okay, for example, if we have a impulse function ft of delta t, impulse function in time domain, so what will be the respective full transform? So it is equals to 1, for example. Yeah, and for example, if we have a DC value, a constant value of a DC with amplitude of a, so its respective full transform is simply 2 pi a of delta omega. And so these are the list of signals, including the rectangular functions. Yeah, if we have rectangular of this equation, so its respective full transform will be this in sync, in the sync function. Okay, and the same things happen if we have a triangular functions up to these symmetrical decreasing exponential functions. Yeah, so these are the examples of signals that that is considered in our table in time domain and its respective Fourier transform equations. Yeah. Okay, so these are the things. These are the content of the attachment. Yeah, attachment. Okay, so let's go back to this lecture. Okay, right. So the next property, sorry, we're going to have a look at the example that actually implies the linearity properties. Okay, so we are having these signals, and we need to actually find out what should be the Fourier transformation for the YT signal. Yeah, YT signal. Okay, so the YT is said to have this form of signals. Yeah, we have somehow a signals in which we can say that this signals is having is basically a summation of two different signal which are rectangular functions. Yeah, we can see that these are rectangular functions. Yeah, which is having a period. I mean, the duration from -2 to +2. Rectangular functions, and we also have a triangular functions here. Yeah, the triangular functions, which is having a duration from -1 to +1. Okay, so note that the rectangular function is having an amplitude of 2, whereas the triangular function is having an amplitude of 1. Okay, so basically this yt can be written as addition of rectangular function and also a triangular function. Okay, so we need to obtain the full transform for this yt signal. So what should be the full transform for yt? So let's have a look at the solution for this example. Okay, so this will be the solution for that example. So we are having these signals just now, which is can be actually split into two, where we have a triangular functions, okay, having a duration from -1 to +1 and the amplitude of 1. And also another one is rectangular function, which is having a duration from -2 to +2 and the amplitude of 2. So we can actually see that if we add this rectangular function and this triangular function, we are getting back these signals. Yeah, hopefully you can view it clearly. Yeah, yeah, the summation of these two signals will then produce these signals here. Okay, so what we have to do now is that we want to apply the properties of linearity to answer this problem. Yeah. So we need to actually obtain the Fourier transform for each of these signal. Okay. Let us try first with these triangular functions here. Okay, this is we obtain this from the table. Okay, we obtain this from the table. If I can refer back to the table, okay, this is the one. Okay, right. So we refer to page number 3. This is the case where we have a triangular functions with the amplitude of A and duration of from negative tau to positive tau. So the equation for this triangular function is given by this, A triangular T over tau. So its respective Fourier transform will be simply A tau sin squared omega tau over 2. Okay, so note that. So note that the case. So when we go back to that solution just now, we know that the amplitude A is equals to 1 and the tau is actually equals to 1 also. So we're going to substitute A and tau in its Fourier transformation. So we can write that this equation in time domain basically will be triangular of T. Okay, triangular of T. And its Fourier transform is simply sin squared omega divided by 2. Because A and tau, both of them are equals to 1. Okay, any question on this? If you have any question, please ask, yeah? Okay, no question at all? Right, good. So hopefully you understand why we choose A and tau equals to 1, because we are referring back to the signals, okay? And from the signals that we have in the table here, we have agreed that A and tau, both of them are equals to 1. That's why we are getting the Fourier transform for the triangular of T is this. Okay, the same things applied for these rectangular functions. Yeah, so if we go back to the attachment at the table, yeah, on the rectangular signals, which is given on the second page, yeah. So these show that if we have a rectangular function in which the amplitude is equals to A and the duration is from negative tau over 2 to positive tau over 2, so the signal is equals to this, A rectangular T divided by tau. So if this is the case, its respective Fourier transform will be A tau sin omega tau divided by 2. So our task now is to identify from the problem what should be the A value, what should be the tau value, so we can then straight away substitute this in its Fourier transform. Okay, so from that understanding, we know that by referring to this problem, we know that the A shall be equals to 2 and your tau shall be equals to 4. Yeah, tau shall be equals to 4 because when 4 divided by 2, we're going to have 2 here, yeah? Okay, so for that, the equation in time domain will be simply 2 rectangular T over 4, and its Fourier transform will be simply this equation, or this term in which we substitute A and tau. So end up we're going to have 8 sin function of 2 omega, yeah, because tau equals to 4, so we cancel out, we're going to have 2 omega. So in Fourier transform, it's going to be 8 sin of 2 omega. Okay, so we have obtained the Fourier transform for these two signals, yeah, separately. So now we can just simply add them together because we are referring to linearity properties in which it said that these signals, its Fourier transform can be simply obtained if we can just add on the Fourier transform for both signals of triangular and rectangular. Yeah? So end up when we add them together in time domain, so its respective Fourier transform will be simply addition of its Fourier transformation. So we're going to have sin squared omega divided by 2 plus 8 sin of 2 omega. Okay, so that should be the solution for first example, which is on the application of linearity properties of Fourier transform. Okay, any question on this? Hopefully you understand this clearly, yeah? on the properties of Fourier transform number 1, which is on linearity. Okay, let us proceed with the second properties, which is a time shifting. So we are having, let's say, we have xt in time domain, and its respective Fourier transform will be x omega. So if this xt is said to be having a time shifting of t naught, yeah, time shifting of t naught, so its respective Fourier transform will be simply x omega exponential of negative j omega of t naught. Yeah, because we have a t naught there, so simply the Fourier transform will be just a multiplication of x omega with exponential term of negative j omega t naught. So if we have a value, I mean the shifting is xt plus t naught, yeah, xt plus t naught. So simply Fourier transform will be x omega exponential of positive j omega t naught. Yeah, we just simply change the sign of exponential terms. Okay, so that is properties of time shifting. So the third properties is the time scaling, in which if we have xt, for transform will be x omega. So let's say now we are having a scale of time by a, yeah, x of at now. So the respective for transform will be simply 1 over a x of omega divided by a. Okay, so again, I would like to stress one more time that all of these properties can be referred to the first page of the attachment table. Yeah, you can refer to the attachment table. So you don't have to memorize all of these. You can just refer to the table to find out what should be the equation. Let's say, for example, what should be the equation of Fourier transform for the case of a signal that experience a time scaling operations. Okay, so hopefully you understand on these properties, number 3 on time scaling. Okay, so to test our understanding, let's have a look at this example. I'm using a rectangular function as an example here. Okay, so we have two questions here. Number 1 is here. We need to obtain what should be the Fourier transformation for the signals. Yeah, for this rectangular function. Number 1 is signals which has been shifted by half unit to the right. Half unit to the right. Remember, yeah, rectangular is having a duration from negative half to positive half with the amplitude of 1. So if you base on this yt, it is said that a normal or original rectangular function has been shifted by half unit to the right, and it has been amplitude scaled by 3. Okay, and for the second example here, rectangular function has been shifted by half unit to the left and amplitude scaled by 2 units. Okay, so we are going to find out what should be the Fourier transformation if the rectangular function do have this kind of signals operation, yeah, which include the time shifting and also the amplitude scaling that we have just now, yeah. Okay, so let's have a look at the solution for this example. Okay, so let's have a look at this solution for that. Okay, this is the one. Okay, so this is the original rectangular functions, yeah, which is having a amplitude of 1 and duration from negative half to positive half. Yeah, this is a rectangular T. We know this from chapter 1 before. So when we refer to the question, this is the one, yeah, that we have. So we know that the equations that represented, yeah, by a operations, yeah, by an operations from original to this new signal is basically this one, which is a 3 of rectangular T minus half. Yeah, half unit shift to the right and amplitude scale by 3. Okay, so now we are going to find out what should be a Fourier transform for these equations in time domain. Okay, so for that we have to refer back to the table, page 2, that we have seen before. And this is referring to the transformation table, and from the equations of the table is given that if A rectangular T over tau, okay, T over tau, yeah, Fourier transform will be A tau sinc omega tau divided by 2. Okay, so we know that If this is the case, we have a rectangular T. So for rectangular T, A is equals to 1, tau is also equals to 1, yeah? Okay, so you can compare, yeah, this value of A and tau. So I think I have to refer back to the table here, yeah? This is table on this, yeah? For rectangular T, A shall be equals to 1 and tau shall also be equals to 1. So that will lead to equations of rectangular of T, yeah? Okay, so for that particular case, its Fourier transform of rectangular T of this, yeah, will be simply sink of omega divided by 2. Okay, so sink omega divided by 2 is Fourier transform for rectangular T. Okay, now rectangular T is said to experience this operation, a shifting and amplitude scaling, yeah. So what should be the Fourier transform for those, for this signal? Okay, so for that, we know from linearity properties, if in time domain, we multiply it with a constant. So in frequency domain or in Fourier transform, we're going to have a same multiplication value. So 3 rectangle T will give us 3 sin omega divided by 2. I'm referring to this equation, yeah? And then it also include a shifting by half. So when you have a shifting by half, you have to use a time shifting properties of Fourier transform. So we have learned previously in lecture that if we have a shifting value, simply we have multiplication with exponential negative j omega of the shifting value. Yeah.
Doctor, in the previous class, lecture 1 and 2, you said that we need to do time shifting before any other
Okay.
property.
All right. I agree with you. But for this particular case, there is no effect basically. Yeah, there is no effect because for this particular case, simply we just multiply the amplitude on this Fourier transform. It doesn't matter. Yeah, so don't worry on that. Okay, hopefully you clearly understand about this issue. Yeah. Okay, so it doesn't matter. So if you want to proceed with the shifting first, should be okay. The answer will be the same. Yeah, the answer should be the same. Okay, so repeat again. So what we did in this example, because the signals is 3 rectangular T minus half. So what I did in this case is the first one is obeying the linearity properties. So multiply by 3 for the time domain will result on the same multiplication for the frequency domain. And we have a time shifting in time domain, which is half. Okay, so in frequency domain, simply we just multiply the previous equation here, which is 3 sin of omega divided by 2 with exponential of negative j omega of the shifting property, shifting value, which is half. So for that, the results of your Fourier transform for 3 rectangular T minus half will be simply 3 sin omega divided by 2 exponential negative j omega divided by 2. Okay, hopefully it's clear, yeah, on this transformation. Okay, for the second example, if you can recall, this is the case. Okay, we have a shifting by half units to the left, and the scale of amplitude is now equals to 2. Okay, so I believe that the equations can be written to be look like this. Okay, you can try to do this on your own, which is 2 rectangular T plus half. And basically we are repeating the same problem as above. The difference is only on the amplitude of the scaling, yeah, the value of the amplitude scaling, and also on the shifting value. Previously is a negative half, so now it is positive half. So the changes will be on the sign of the exponential terms, yeah. So we are supposed to get 2 sin of omega divided by 2, and the exponential will be now positive of j omega divided by 2. Okay, hopefully you are now clear regarding the amplitude shifting, time shifting properties of Fourier transform, yeah. Okay, so let us go back to this lecture. Okay, so we are having a second example, I believe. Yeah, this is the one. we are having a triangular functions. Yeah, so there are two questions in this example, this page. The first one is a triangular which is having an amplitude of 3 and duration is from -3 to +3. Second example is that we are having a amplitude of 3, but basically the signals has been shifted, yeah, has been shifted to the right, yeah, in which I can say that is basically shifting from the above equations, yeah, which is a shifting by 3 units based on this equation to the right. Okay, so we are requested to find out what should be the Fourier transform for signal number 1 and signal number 2. Okay, so for this, knowing that we are referring to the triangular function, so you have to refer to the table of Fourier transform, which is having, which indicates a transformation of a triangular functions, yeah? So let's have a look at the solution for this example. Okay, so we are having this triangular function. All right, so from our chapter 1 last time, we know that this is the triangular functions, yeah? Triangular t, in which for triangular t, the amplitude is 1 and the duration is from -1 to +1. Okay, so that will give us a triangular t equation, and that can be referred to this table of attachment. Okay, I'm referring to the third page of this attachment. Okay, this is the case. Basically, for a triangular t, your A amplitude will be equals to 1 and your tau will be also equals to 1, yeah? So basically, you're going to have equation will be triangular of t only, yeah? Right. But now, when we refer to the questions, okay, this is the questions. We can see that the amplitude has been scaled to 3 and the duration of the signals is from -3 to +3, in which it experienced a time scaling, yeah, time scaling. So for this, we can see that the equations that lead to the formations of this signal from the original triangular t is this one, which is a 3 triangular of t divided by 3. Yeah, 3 is the amplitude scaling, and since we have what can say the expansion of the width of the signal to 3, basically it seems before this is 1, -1 to 1, but now since we have a new expansion from -3 to +3, so that will involve basically a scaling of time, yeah? So it will be 3 triangular of t divided by 3. Okay, so from here, we know that there should be 2 operations involved or 2 properties involved. The first one is linearity, yeah, when we have a multiplication with 3. And the second properties involved is time scaling, yeah, time scaling. All right, so now we can simply find the Fourier transform for the 3 triangular t divided by 3. This is this time domain signal. So we are referring back to a table, yeah. This is the equation which is extracted from the table, yeah. So when we have a original triangular function, which is a and tau, both of them shall be equals to 1. Yeah, so we're getting triangular t, its respective Fourier transform will be simply sin squared omega divided by 2. Yeah. All right. So now from this triangular t, we can find the Fourier transform for this signal. Yeah. Okay. So what I did here is I'm using the linearity properties. So you can also start with the time scaling, no problem. Yeah, but the answer should be the same. Okay. So we have a 3 triangular t, linearity properties will give us also multiplication with 3. So 3 sin squared omega divided by 2. So I'm using this one, yeah. Initially, triangular t will give us this. So 3 triangular t will give us 3 sin squared omega divided by 2. Okay, now we can straight away use a time scaling properties. Yeah, we can refer to the notes, yeah, when we have a 3 triangular t divided by 3, okay, and up we are going to get 1 over a, yeah. Imagine that our a, our constant a, is equals to 1 over 3, yeah. A will be equals to 1 over 3. So for that, its Fourier transform will be 1 over a, yeah, A is 1 over 3, sin squared omega divided by A, yeah, omega divided by A. So all the terms omega will be substituted by omega divided by A. Yeah, since we have A is 1 over 3, yeah, in this case we have omega over 2, right? So we have omega divided by 1 over 3 divided by 2. So this 2 and this 2 is the same. So we have a changes on this omega, which is now omega divided by A. So further on, when we multiply this equation here with 3, we're going to have 9 sin squared of 3 omega divided by 2. Okay, so this will be a Fourier transform of 3 triangular T divided by 3. Okay, any question so far on this example? Any question on this example? Okay, so to get it clearer, to make it clear for us, let's have a look on this scaling of time. Remember, this is the equation, yeah? If we have f of at, a is a constant, respective Fourier transform will be 1 over a, right? A modulus, all right? Okay, and we have a transform of omega divided by a. So all the omega terms shall be now substituted or replaced by omega divided by a, as what we did in this example here. Yeah, previously you have omega terms in this bracket, yeah, in this bracket which is omega divided by 2. So since we have the a, which is 1 over 3, so we have to divide the omega with 1 over 3. It's not. Okay? All right. Hopefully you are clear about this example. So let's have a look at the second example. If you can recall back, this is the case, okay, where we have a triangular function which is now having a duration from 0 to 6 with the amplitude of 3. So by using a time shifting, I mean the time-based operations, you can prove that these signals basically, which is originally from the triangular t, it will be 3 or triangular t divided by 3 minus 1. Okay, because initially it is a triangular function which is having a duration from -1 to +1. So first thing first, we're going to shift it by 1 units to the right. Yeah, 1 units to the right. So that will be from 0 to 2. And further on, then only we can have a shifting, a scaling by 1 over 3, which will lead to a new duration of signals, which is from 0 to 6. So you can prove this on your own, that from triangular t, by having this operation, yeah, time-based operations and amplitude scaling of 3, we are going to get these signals. Yeah, so you have to show this or prove this on your own, that you are going to get these signals, yeah, given in the questions. Okay, so this is from the previous example that state if we have a triangular t in time domain, its Fourier transform will be sin squared omega divided by 2, yeah? Okay, so what we did here, few examples, few operations will involve in these solutions, yeah? We have 3 operations, 3 properties to be considered now in these questions. So from these signals, the properties are linearity, a shifting of time, which is 1, and also a scaling of time, which is 1 over 3. So these 3 operations, these 3 properties involved, yeah? So those properties that have been learned so far will be applied in this example, yeah? So what I did here is I'm starting with the shifting of time. So I can also start with the linearity 3 just now, yeah, but just mathematics 3 should be okay, no problem. Yeah, so you can start with 3, which is amplitude linearity properties. Yeah, that should be okay. Or you can also start with the shifting. Yeah, but never start with the scaling. Yeah? If you have a shifting, never start with the scaling. Yeah, you have to start with shifting all the time. So that's why in this case, I start the operations with the time shifting. So for this case, so we have a triangular t minus 1. So initially it's this one, yeah, triangular t will give a sin squared omega divided by 2. So when we have a time shifting by 1, which is triangular t minus 1, simply we are going to multiply this sin squared omega divided by 2 from the above with this exponential. of negative j omega of the t naught or 1, yeah, because a shifting by 1 will lead to this multiplication with exponential of negative j omega multiplied with 1, yeah. Okay, then only we can proceed the time scaling. Now we have a time scaling by 1 over 3. So as previously learned, yeah, when we have a shifting by 1 over 3, we're going to have 1 over the scaling constant. Yeah, so scaling constant is 1 over 3. So we have 1 over 1 over 3. Sin squared. Okay, so all of the omega terms shall be divided by 1 over 3. Yeah, this is from the properties of time scaling. So all omega terms need to be divided by 1 over 3. So we have omega, this omega divided by 1 over 3. And this omega, supposedly, sorry, I missed something here. This omega supposedly shall also be divided by 1 over 3. Yeah, by 1 over 3. So end up, by solving these terms here, we are going to get what? We are going to get 3 sin squared. This will be 3 omega divided by 2, and with that, we're going to have exponential negative j of 3 omega. Okay, yeah, so hopefully you're clear about these issues. I repeat again. So when we have a time scaling, yeah, time scaling properties or time scaling operations, in this example is 1 over 3. So we are going to have 1 over a, and all the omega terms shall be now divided by the constant of 1 over 3 as shown in this example. So that will be the answer after we completed the time scaling properties or operations. Yeah. So end up finally with the linearity properties, which is a time amplitude scaling. So we have to multiply simply by 3. Yeah. So end up going to have 9 sin squared 3 omega divided by 2 exponential of negative j of 3 omega. If we start with the amplitude scaling, your answer will be the same. No problem with that, yeah? Okay, any question on this example so far? No? Okay, yeah, so if there's no question, I think we can proceed now with the next properties, I believe. Okay, again, we have another example, sorry. So if we base on this example, basically we are repeating the first example that we did in this slide and in this lecture 10. Based on this, we notice that these signals of ft is a summation of two different signals. The first one is this rectangular function, rectangular function, which is having a duration from 0 to 6, okay? And the other one is a rectangular function also, which is having a duration from 2 to 4. And each of these signals are having same amplitude of 2, yeah? So for the first rectangular, we're having the amplitude of 2. And also for the second rectangular function, we're also having the amplitude of 2. Okay, so I think it's good if we can have a look at the solution for this example, just to ensure that we really understand on these properties of Fourier transform that we have learned so far. Yeah? Because if we base on this example, it involved the properties of time shifting and also time scaling together with the amplitude scaling properties, yeah, or linearity properties. Okay, let's have a look at the solution for this example. Yeah. Okay. Okay, so this is the case where we have these signals here. So as what I've told you in class lecture just now, it is basically addition of two signals. The first one is rectangular function, which is duration from 0 to 6, amplitude of 2. Second one is this rectangular functions from 2 to 4 durations with the same amplitude of 2. Okay, so the thing that we have to do now is basically is to obtain the equation in time domain for both signals here, yeah, for this signal number 1 and signal number 2. And I think you can obtain the equations in time domain for both signals here on your own, I believe, because we have been learning this topic in chapter 1. Yeah, so I'm hoping that you won't be facing any problems of getting the equations for these signals in time domain. Yeah. So supposedly, yeah, you are getting for the first signals here, it should be 2 rectangular t over 6 divided by minus half. Okay, how to get this? Again, I left this to you to find out on your own. Okay, and the same things applied for the second signals here. It's supposed to be 2 rectangular t divided by 2 minus 3 over 2. Okay, so that should be the equations in time domain for both signals. And based on this, we note that there are 3 operations involved for both signals. It involves time shifting, it involves time scaling, and it also involves the amplitude scaling. Yeah? Okay, so now let us try to find out what should be the Fourier transform for the first signal and the second signal, because we can apply the linearity properties to solve this problem, in which what we have to do is simply find the Fourier transform for this signals number 1 and Fourier transform for the signal number 2, and finally we just add them together to find out what should be the Fourier transform for the ft. Okay, so for this you have to start with the rectangular function, because this is a basic function for the questions here. So rectangular t, Fourier transform will give us sinc omega divided by 2. I think we have learned this previously. All right. So in this question, I start with the amplitude scaling, linearity, so it doesn't matter. It is also correct. Yeah. So I start with linearity properties, which is a rectangular, with this amplitude scaling multiplied with 2. So 2 rectangular t will give us 2 sinc omega divided by 2 based on this equation. And afterwards, I'm going to proceed with the shifting of half. Yeah, shifting of half. So basically, for the shifting of half in time domain, its respective Fourier transform will be simply 2 sinc omega divided by 2 exponential negative j omega divided by 2. Yeah. So a shifting will then we need to add exponential value of negative j omega divided by 2. Yeah. And finally, we have a scaling of 1 over 6. Yeah, 1 over 6. So as what we have learned previously, to cater for this scaling of 1 over 6, we're going to have 1 over the scaling constant, which is 1 over 6, sinc function of omega, and so this omega shall be divided by 1 over 6 divided by 2, and the same things applied for this omega, which shall also be divided by 1 over 6. Yeah, so this is to cater for the effect of time scaling of 1 over 6. So end up, we're going to have what? We're going to have the final Fourier transform for signals of 2 rectangular t over 6 minus half will give us this, which is 12 sinc 3 omega exponential negative j of 3 omega. Okay. And the same things applied for the second second rectangular functions. You can have these. You're not going to touch this briefly, so you can have a look at these solutions later on. But it's the same as the previous example. It will be the same. So end up we're going to have the Fourier transform for the second signal, and based on linearity properties, the answer for Fourier transform for ft will be simply a summation of the first Fourier transform and the second Fourier transform, which will be this one. Okay, so that will be the answer for Fourier transform of the ft. Right, so let's have a look at these example. Okay, the next properties to be covered in this lecture is frequency shifting and modulation. Okay, so in these properties, if we have xt, which is Fourier transform is x omega. So if xt is said to be multiplied with exponential terms, which is exponential j omega naught t, so we can see that its respective Fourier transform is simply a shifting in the frequencies value, in which we are getting the x omega minus omega naught. So this is what we call as frequency shifting. Yeah. So this frequency shifting is obtained when we have a multiplication of the xt in time domain with exponential of j omega naught t. So if we have a multiplication of xt with exponential negative of j omega naught t, so we are going to have x of omega plus omega naught. Okay, so we just simply change the sign, yeah, for this frequency shifting constant, yeah. Okay, and then continuation from this frequency shifting, we can also have a case whereby the xt is said to be multiplied by a cos omega naught t. Okay, so cos omega naught t basically can be written in terms of exponential j omega naught t. It can be written by using the Euler's relationship. Yeah, we have learned this in chapter 2 before. So by that, we can get that if any xt function multiply with a cosine omega naught t, its Fourier transform is simply half of x omega minus omega naught plus x omega plus omega naught, in which xt its original Fourier transform is x omega, xt is original Fourier transform is x omega. So for the xt, which is multiplied with the cosine omega naught t, so notice that there should be omega naught there. So its respective Fourier transform is simply half. So the x omega just now shall be then shifted by these two values. The first one is omega minus omega naught, and the second one is omega plus omega naught. A shifting of x omega to the right and x omega to the left. Okay, so this is the case of multiplication of xt with cos omega naught t, and this properties is called a modulation. Yeah, a properties whereby a signal in time domain is multiplied by trigonometric terms, whether it is cosine omega naught t or sine omega naught t. So for sine omega naught t is given down here, so you can read this on your own. But these properties, I repeat again, these properties, which is a result of time domain xt multiplied with the trigonometric terms, is called a modulation. Yeah, so we are going to see this more or frequently in lecture 12. Lecture 12, when we learn about the application of Fourier transform, specifically on the application of modulation later on. Yeah. Okay, so this is the fourth properties that we have learned today, which is a frequency shifting and modulation. So I combine them together. Yeah, I combine them together because both of them are interrelated. Yeah. Okay, so this is the example, which is actually to test our understanding on this modulation and also on frequency shifting properties. But I'm not going to do all of these examples. I only choose part of it. Yeah, so let's have a look at the solution for these few examples. I think I made for the first example, for the third example, so it should be third, yeah, number 3 here, should be a third example for the for the fifth and for the sixth, I believe. Yeah, the rest you can do it on your own because it's similar to what we have done in the examples, yeah, in this case. Okay, so let's have a look at the solutions for these examples here, which is to test our understanding on this time, on the modulation and frequency shifting properties, yeah. Okay, and let's have a look then. This is the case number 1. Okay, number 1 is this we are having this xt function, which is 2 exponential negative j of 2t plus 3 exponential j of 3t. Okay, so we are having two signals here, exponential negative j 2t, exponential j of 3t. Okay, so basically, this can be referred to the table. Specifically, you can refer to the table on page number 2, I believe, which shows us about the exponential term. So if I can refer back to the table here, second page, I believe, signal number 1, 2, 3, 4, 5, 6, number 6, yeah, where we have the exponential terms of j omega naught t, yeah, exponential j omega naught t, yeah, sorry for that. Yeah, exponential j omega naught t, this is the one. So its respective Fourier transform, of frequency domain will be 2 pi delta or impulse function, yeah, 2 pi or impulse function, omega minus omega naught, omega minus omega naught. So we have exponential j omega naught t, so respective for transform is this. So if we have exponential negative j omega naught t, simply we just change to omega plus omega naught, yeah. So I'm using this transformation from time domain to frequency domain to answer this question. So for that, we refer to the table. So exponential j omega naught t will give us this. So by right, if we have 2 exponential negative j2t, so the Fourier transform is simply 2, because this is a multiplication with a constant, yeah, amplitude constant. So it's 2 and 2 pi delta omega plus 2, okay, because we have negative j2t, so we have this equation or this term. And whereas for the second term, which is 3 exponential j of 3t, Fourier transform will give us this. 3 is a constant, multiply with 2 pi impulse function omega minus 3. So we have a 6 pi sigma omega minus 3, yeah? Minus 3. Okay, hopefully you are quite clear related to this example. So basically, if we just add them together, yeah, if we just add them together, because it is based on linearity properties, you are getting these equations, yeah, 4 pi delta omega plus 2 plus 6 pi delta omega minus 3. So this is to obey the properties of linearities, yeah, the first properties that we have learned. Okay, so let's have a look at the second example, sorry, the third example, which is 4 rectangular t of cosine of 4t. Okay, so if we base on this, notice that in this case, our interest is these signals. The signals of 4 rectangular t is multiplied with a cosine function. So now we can actually apply the properties of modulation. But first thing first, you need to obtain what should be a Fourier transform for the 4 rectangular t. Then only you can apply the modulation properties. Yeah. So for that, from what we have learned in previous example, if we have rectangular t, so we're going to have sinc omega divided by 2. Yeah. So this is what we have learned previously. So if we have a 4 rectangular t, we are going to get 4 sinc omega divided by 2. Okay. So this 4 rectangular t is said to be proceeded, yeah, should be proceeded with the modulation properties, which is multiplication with a cosine of 4t. So for that, we can write that 4 rectangular t of cosine of 4t. Okay, so this will be the basic signals. So that will lead us to this result, which is half 4. Okay, this is the same function will be applied, but all the omega terms shall be then shifted. Yeah, all the omega terms shall be then shifted. You're going to have a shifting to the right, which is omega minus 4 divided by 2, plus a shifting to the left, which is sinc omega plus 4 divided by 2. So this is a properties of modulation. Yeah, properties of modulation, which is, if you can recall back, it is half x omega minus omega naught plus half x omega plus omega naught. So that should be the results of your modulation properties for this particular signals here. Okay, any question on this example? Is that clear on this? Hopefully okay, yeah? Okay, next will be on the, I think should be on the 5th questions, where we have a 3 triangular 2t cos 4t. So the same things apply, in which our signal of interest is this one, which is the triangular 2t. Yeah, so we have to find out what should be the Fourier transform for this. And later on only we apply the modulation properties, because we have a multiplication with a cosine of 4t. Okay, so 3 triangular 2t basically will give us this, yeah? 3, yeah, 1 over 2, because why 1 over 2? Simply because we have a scaling by 2 units, yeah, scaling by 2 units. This is scaling scaling constant of A, yeah, so we have 1 over A sin squared omega divided by A, yeah, omega divided by A. So you can refer to the table on these issues, yeah. So basically we're going to get this 3 over 2 sin squared omega divided by 4, and by applying the modulation properties end up going to get this, yeah. Remember, this is the basic terms to be applied. So when we have a multiplication with the cosine of 40, simply all of these terms need to be shifted by 4 units to the right and 4 units to the left as shown here. So we have a half x omega minus omega naught plus half x omega plus omega naught. Yeah, so this is the results of modulation. So finally, we are getting this equation as the final Fourier transform for these signals here. Okay then, and finally, this is the examples for the same slide. Yeah, we have 3 triangular t over 3 cos of 2t plus cos of 5t. So I believe that for the first term here is similar to the previous example. The difference will be only on the scaling constant, which is 1 over 3. So I believe that you can try to solve this on your own, find out on the solution for that. And for the cos 5t, should be, it is simply pi of delta omega minus 5 plus delta omega plus 5. Okay, for the cos 5t, you can refer to the table here. It's given by this, yeah, cosine function. When we have a cosine omega naught t, so its respective Fourier transform will be simply pi delta omega minus omega naught plus delta omega plus omega naught. That's why we are having for cos 5t is given by these equations here, yeah. Okay, so what you have to do is to find out the Fourier transform for these terms. Yeah, once you get the answer, simply the answer for Fourier transform for xt will be a summation of the first Fourier transform and the second Fourier transform. Okay then, is that clear on these issues? Any question on this? Nope. Okay, if there's no question, I think I'm going to stop here. So this example will be done tomorrow on our lecture tomorrow. So I believe that we have more than half an hour. So we're going to have a second quiz today on the Fourier series. Yeah. So we can start on. I have to show you the quiz question. I'm going to upload the question in the Google Classroom now. Yeah. Okay.